Hello. Fetch these. Updated weights and biases. Is required. Might as well treat it as weights and biases. It's the first one, so we read that here. The next one here, outputs 1, is then outputs. So 1 is outputs, 2 is loss, and 3 is residue. So I can do this again then. No, I use this. See if this still works. Nope. What did I do wrong? I don't see the problem. There is no problem. Yep, it all behaves exactly the same, so that is good. I wanted to automatically stop as soon as the prediction is correct. I think that means that the loss is less than a quarter. I better look at the residual maybe. The residual must be less than the absolute value of the residual, I guess. Must have a sign that is corresponding to the labels. Yeah. And apparently, if this one is +1, labels is +1, then this one is negative. So we have 1, negative, 0, positive, 1, negative, another 1, negative, 0, positive, 1, negative, 0, positive, and 2 negatives for 2 1s. Yep, that would be the good thing. Labels and residual. Run over all the 9 samples that we have. And then get the prediction. And the target. The target is, well, just a label, let's say. How do I get the label? I have a labels tensor here. Could use the flat thing, but I think there's a vector as well. Seems the most logical thing to do then. You can find back.flat, tensor flat, yeah. Just, I think there's a tensor vector. Nope, Equivalent. Pull request. Yeah, just a map then. A tensor map for floats from a two-dimensional array, I think. And this thing is a one-dimensional array. So I can do labels tensor float 1. And prediction is no, I need a value from as a dual. Output also returns a tensor. I'm literally making a map here as well. Thought it was different. Residual, that's the difference between the prediction and the target. And I saw that if this is 1, then that one's less than 0. Whatever. So if this is less than 0, then we predict true, and then the label must be 1, which is also true. This is also a float though. It's kind of scary to assign that to a boolean. Let's make this as well less than 0.5. It's the other way around. Now it's true when it is 0. So this must now be larger than 0. Nope. Asking for tensor of 1 dimension from a tensor of 2 dimensions. Oh, so lame. It thinks that this is a two-dimensional thing. Maybe I should reshape it to a one-dimensional one first. Or I can just do a 0, comma. Let's do the 0, comma thing. Yeah. 2 dimensions. What the hell? I think I got the sign wrong. Because it immediately terminates. No, that would be impossible. Yeah, negative, positive, negative, negative, positive, negative, positive, positive, 0. What? 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, the last one is a bit vague. So let's call it not negative. So that is the one. It's apparently then interpreted as a negative. Well, whatever. This is not what I wanted. The main reason I would say is that this one is super far off. It really has to be close to 0. This one is far off. Now I'm confused. Doesn't even draw any line. Sorry, I have to think. What the hell? How much is this squared? Calculator. 0.9976 32563 squared. Yeah, it's that number. Okay, so it's more like this isn't a residual. Oh, of course it is. Sorry. Yeah. So difference between 0 and 1 with the output of a sigmoid function. So the result is then between -1 and 1. But the only moment that they really are, when the prediction is the same when the absolute value is small. Sure, this is a good prediction. This is a bad prediction. It doesn't even matter if it is positive or negative. The absolute value is just too large. And I guess that the half for the absolute value is the best thing. It's like where toggles. So I take the absolute value of this and you get a value between 0 and 1. 1 is wrong, 0 is perfect, and then a half is kind of the boundary. And then I square it, then you get a quarter. So I want the loss to be less than a quarter. I think that's a trick here. That I don't even have to look at the level, at the target. I already have that tensor map for loss. That is tensor map 2. So now it should automatically stop as soon as it has a good prediction. What happened? Yeah, that's shocking. Everything is below a half. The loss is a value below a half everywhere. That's not what I wanted. It had to be a quarter to begin with. But also it was extremely far off still. No, it's okay. Now it was okay. Hello, Shy. She's getting closer to red here until it goes over it. And at that point all the reds are below the line and the greens above it. It seems to work, but I'm not convinced yet. It's Daryl, yeah. I can give you a new invite, but it's basically dead. Let me find Discord. But yeah, let me find an invite. Think like this. Um, oh, you're already there. It's pretty slow, huh? Yeah, that's an interesting one. I don't think it's ever going to stop here. So this green one is still below the line, so the line should rotate down. But it doesn't because, well, it probably does, but it's gonna take a billion years. It's just too slow. Or maybe it doesn't. Getting closer to this line means getting closer to this green one and getting closer to this red one, and eventually even getting pretty close to all the other red ones. And it doesn't really like to get closer, I think. Well, not until the weights have been blown up to very large values, which might be happening. I'm not sure. Weights, oops, the weights and the bars, yeah, it get larger. If all three, there's two weights and a bias, if all three are multiplied with the same constant, then the line doesn't change. It's just the same line. But if you multiply with the same constant, then the sigmoid function gets narrower and narrower until it becomes a step function. So say this distance is, the vertical distance is put through the sigmoid function. So if that becomes a step function, then it cares less and less how close it is. I mean, below is below, and yeah, it's step function. So as soon as it is below it, then it is a perfect prediction. Even stopped over a million iterations. So I think that in a million years, then this would have been blown up very large, maybe, and then it would have not have minded to rotate. But on the other hand, by the time it is a step function, I'll run it again. By the time the sigmoid has become oh, this is a different one. Sorry, it's random. Well, erratic. Wow, this is a nice one. It's almost vertical. I mean, the rate, let's say, the rate at which it is drawn towards, well, in this case, this green one, which is still wrong. Green must be above the line, red below the line. So only this green one here at the far right is wrong. But the rate at which it is drawn through that is proportional to the derivative of the sigmoid function. So the sigmoid function is the distance from this point to the line is so large that the output of that sigmoid is horizontal. It's just 1. So the change of rate is 0 also. So it does rotate towards it, but so slow that it's never going to happen. And I think that at the same time, it doesn't like to get closer to this one because, well, we have a sigmoid function here as well, but this distance here is a lot smaller, therefore it's not quite 0. Let's say maybe 0.0001 or something like that. And if it gets closer, then that value gets larger. So and then the square of that is counting towards a loss. So it doesn't want to rotate further this way, because then this loss becomes significantly larger, while that one still doesn't count at all, or doesn't change at all, I should say. The loss is 1, but how do we fix this? I think using the sigmoid is just wrong, clearly. But I'm trying to think of another way, actually. See, this is the far point. So the loss of almost all points is near 0, except these two, where the line is cutting through. So the line was cutting through this, between these 2 points here. And if it rotates more horizontally, so it rotates clockwise, then these two values get larger. And this value gets smaller. But even if these values get 0.0001 larger, that's already worse than this one getting 0.000001 smaller. Now, eventually, there's a lot to gain. You can move this one near 0 as well. So maybe if you rotate the line to the correct position, then this becomes maybe 0.01. And this one too, let's say. So then we would have, I don't know, 100th more. But this one would be 100 times smaller. It goes from 1 to I don't know, 100. So I think that what should happen here is that it says, okay, I see that my loss here gets larger if I rotate the line, but I don't care. This one is way more important. Way, way, way more important. How can we change that? I've been getting a gradient out of this as well. Maybe do I get a gradient per point? Yes, we do. So I'm getting a gradient per weight bias, that's 3 values per point. So I could draw a matrix of 3 by 9. That shows me the gradient influence on each of the weights per point. I would like to see that if I have it. Let me find that. This is already summed. I have a gradient here, but only for the elements of the weight. Looks two-dimensional here, but well, we have only one output. So this is actually has a dimension of 2x1. Well, 3x1 because I also have the bias in there as a weight ish. But the gradient here pops up for the first time without being per input point. I'm going to have a look at the README, I think. So if you're afraid of mathematics, then please leave now. The gradient. Oh boy. We don't even talk about a gradient unless it's delta of W already. This is we're talking about a gradient relative the gradient of the loss function relative to the weights, with the loss function already encompasses, if that's the right word, all inputs. So we don't have a gradient per input. Otherwise, I could count the gradients for the points with a huge loss more heavy. I think that theoretically would mean that I just multiply z with itself. No, that not z minus t. I wonder if, in the end, the total gradient is not just the sum of the gradients per input point, training point, I should say. mean, why already sum here? Why not just first calculate gradients and then sum everything up? But I'm not convinced that is the case. It's kind of strange, isn't it? I mean, the loss function is perfect. The minimum value of this loss function means a perfect prediction, yet it doesn't find it because it just, if it is too far away, and then the error is as it were flat. I mean, this is so, for certain points, this is so much near 1 that I mean, the t is 0 or 1, it's just a constant, it's the label, and the output is the output of the sigmoid function. So if you're too far off, then this is just almost a constant output of the sigmoid function. It's like this little thing. So in the end, it just runs horizontal, or in the beginning. And if it runs horizontal, there's no slope. So it's going to say, yeah, that's as flat as it is in the middle. Maybe I am in the middle. In other words, the whole sigmoid function ignores points, that completely ignores points that are way off, because then the rate of the learning rate is way too small for those points. So it tries to optimize the neural network for not the points that are far off, but the points that are already getting close to the correct value, and it just doesn't work. It just doesn't work. It should do the other way. It should do something else. It should optimize first for the points that are most off. I could just change the sigmoid function to the ReLU. It's what's up, a rectifier thing. So that's instead of a step like this, we just go horizontal. It's just 0, and then when we get at the 0 input, we make it linear. Then, because it's linear, the further away, the more heavy it counts. So it's the grade of not more heavy. The gradient is the same everywhere. Hell, I would even make it a parabolic. That would be even better, I think. So flat on one side and then parabolic on the other side. And that means that the further you're off, the faster you want to go down. It sounds better in my eyes. And they also have a sigmoid function that doesn't go flat. So at least then you don't get stuck. So that's like, if you can see my mouse, hope. So the sigmoid function is like horizontal, and then goes like this, and then horizontal again. Let me find the picture again. Really? Why is this still here? I left the program. Oh, that's, what? Oh. Yeah, I wanted to show this one. So here you see the sigmoid function is the green one, and then the purple one is the derivative of that. So you, at this point it's the highest. The purple thing is a quarter, so that's because it is steep here. And then we go further, it gets less and less steep until it's horizontal again. So then the derivative is 0 again. So in terms of derivative, it has no clue if you are here or there. If it's very good or very wrong, because in both cases it's just horizontal. Yes, I sound Dutch because I'm Dutch. And then you have activation functions that are sigmoid-like here, but they don't go completely horizontal. They keep going, let's say, like this, straight line up and up and up and up. So you never really go to 0 here. And this is the ReLU activation function that I think will work much better, because that just has a constant slope if you're off on one side. So instead of using that, if you use this one, I think it's going to work a lot better. You can find the name of that other thing. I saw a few of them. Not really. They cut this one off before the runs horizontally. I think I want to add uh, I changed the activation function to the sigmoid plus a very shallow line, like almost horizontally, but at least that it keeps going up on one side. So then you end up with almost the same thing, but then here it doesn't go horizontal, it just keeps going up at least. It won't or can't fix it completely, but it would be interesting to see the effect, I think. That's some really weird shit here as activation functions. Like the green stuff looks like a normal activation function, so no, not this one. What the hell is red? Error. Oh, poor dreaming warlord. What is going on? You watch a nightmare movie from Disney. Yeah, don't watch Disney. Um, random guess. Instead of using sigmoid, we use not just sigmoid of sum, but we multiply sum also with a very small number, and then I add that to the sigmoid function. It's not enough because you also have to look at the derivative, but let me check if this compiles. It compiles. Now I want to know what happens if I run this. Immediate. Not. It doesn't like it. Not at all. Can I understand why? I guess the reason is that the outputs get larger than 1. But how does that exactly result in not a number everywhere? Because my weights were updated with not a number. The gradient was not a number. Something went completely wrong. Completely wrong. Yeah. I have no idea why, but okay. But why not? I can use this as an activation function if I want to. Can't I? You get subtract outputs minus labels. Yeah, that's not really correct anymore, I guess. I think this has to be clamped. Difficult. If now the output goes even beyond the prediction, so it can be larger than 1. So leave the label as 1. Well, I say it wrong. The target label on target, same thing. If that is 1 and the prediction is larger than 1, then it's a good prediction. But the residual becomes larger again, and then the loss is the square of that. So the square of the residual. So if you go, we have an extremely good prediction, goes even beyond that point, and then we count it as a loss again. That's why I have the feeling that this is definitely not good, right? Yeah, no, it's not. I don't think I should mess with the residual and how the loss is calculated, really. Should I? Could take a different loss function. Difficult. Nope. I have to think about this. And on stream is not a good time to become silent and think for half an hour. Prefer to do that while I try to sleep. Maybe that's why I'm laying awake every night. But yeah, no. Let's just Google for it. Let me undo this. Nope. I don't want to do this. Just keep my sigmoid. No, the problem isn't even here. This is forward propagation. The problem isn't even really here. I thought I had a comment that said forward. Yeah, forward propagation. This can also be deleted. The real problem is in the backwards propagation, that we don't learn anything because it doesn't see the difference between 0 and 1, which is because the derivative of the sigmoid is this, where the z is the output of the sigmoid. So if it's near 0 or 1, that's symmetrical, but which is just, you saw the graph. Graph's gone. Sorry, no graph. So what I wanted is that this thing is still positive when it is wrong, and wrong being 1. So even if we get in the neighborhood of 1, it shouldn't go to 0. Yeah, that's what we want. But even if I would do something like I take the ReLU function, activation function, I just have to change the loss function completely. I'm gonna ask ChatGPT because I only know keywords and I have no clue. I think this is what I'm running into here. The vanishing gradient problem. So I'm on the right track, that since I suffer from the vanishing gradient here, that I want to use a ReLU, but yeah, you can't really do that for the final output. It says, and I agree with that. Yeah. All those typos. Just not change the activation function, but change the loss function. Apparently. More. Guess it kind of makes sense. You take if I just changed the activation function and the values became larger than 1 and all hell broke loose. But if I do anything to the loss function, that doesn't have any effect. I mean, I can just add a penalty like crazy, and it's still good, right? Yeah, of course. That's what I should do. Yeah, okay. These enter the class imbalance by focusing more on hard misclassified examples. It downweights the loss assigned to well classified examples, allowing them all to focus more on hard examples. The loss landscape to provide stronger gradients for misclassified examples, thereby encouraging the network to adjust its parameters even in cases where this down-net cross entropy loss provide minimal gradients. Again a typo. I meant to type cross entropy loss, of course. If you if you input please into this neural network, the output is certainly. Every time you say please, it says certainly, as if it is totally happy. Thank God, finally a human who appreciates me. Or who is polite, I guess. The standard binary cross entropy loss can be mathematically described as follows. Suppose we have a binary classification problem, red-green, with the following: y is the true label, 0, 1, red-green. Y cap is the predicted probability output of the sigmoid function, that the label is 1. Yep. So a perfect 0 means that it is 100% sure that it is the 0 label, and a perfect 1.0000 means it's absolutely sure that it is 1, but when it's half, it doesn't know. The binary cross entropy loss for a single example is calculated as the loss of label and the current predicted output function of is, I'm not using that. Y times the log of y cap plus 1 minus y times the log of 1 minus cap. Okay, since y is exactly 0 or 1, we just get either this term or the other one. Say y is 1, then this drops out, and it just minus the log of y cap. And then if y cap equals y, it is exactly 1, then we get 1 times the log of 1, which is 0. So we have no loss. And it's symmetrical for the y is 0, of course. But if it deviates, then this becomes less than 0. Cannot get larger than 0. It's always between 0 and 1. So then you take the log of something that is less than 1, which means that you get a negative exponent, and then that grows with the minus, it becomes positive again, and then we have something that exponentially grows, I guess. Not really. Let's see, inverse, right? So suppose we have so if it should be 1, but you have 0.1, that's pretty far off, then you get a very, very negative value here. So if the y cap goes to 0, then it's not exponential, but I think it can grow. Well, actually, no, the log, yeah, it's still a log. No, it's not growing very fast. But if it is, let's say the log is a 10 log, and you have a y cap of 0.000001, then you get a loss equal to the number of zeros. Um, it's not a function of L itself, like the other ones. It's actually trivial. So y is 1, this is 0, and then you get 1 over y cap, which is just the derivative of the logarithm. But okay, maybe a graph still show something that I... It's not in one graph, damn it. Hmm. Yeah, okay. So the input value, this case y hat, is exactly between 0 and 1. It cannot go larger than 1. It's the probability or the certainty that it feels about the prediction. So 1 means it's 100% certain that it is a 1, and 0 means it's 100% certain that it's a 0. But I stated y is 1, so this would be 100% certain that it is something that it isn't, because it is 1. So if it's 100% certain that it is a 1, while it is a 1, then the loss is 0. That's namely correct. And if it's more and more certain about that it is a 0, while it isn't, then we get a huge loss, which goes to infinity in the end. And then the derivative is minus 1 over a y hat. So very steep here, but negative slope. And then almost, but not quite horizontal here. Which means that, let me see, if we are off, I think, yeah, so I think what I'm dealing with is really on this side here. So instead of having a derivative of 0, we have a huge gradient here. It's like, oh my god, please fix this. Much better. I should try this one. Maybe don't even need the weighted binary cross entropy loss function. Gee. Kiras. Yeah, where? Okay. The thing is so Python happy. And then suddenly a 3-year-old again. This is so stupid. There isn't a direct equivalent of. Here's how you can implement it. Call this is sick. What? Sigmoid cross entry. What? Excuse me. I don't think I saw this one before. No, not really. Nah. I think I'm going to. What is this about? Oh yeah, that's that we came from here, I think. It was still llama. The GGML. It's so annoying. They have softmax and they have sparse. What happened to the? Maybe I should look at the C. Cross. Let me see the. Nope. Nope. Cont to data. But yeah, it could be in the same directory as sigmoid. I don't see sigmoid here well either. Really strange, right? I mean, Relu is here. Why is sigmoid not here? Does not make any bloody sense at all. No, there it is. Where are we now then? In math. Okay. No cross here. Cross. There is a cross, but it's probably not it. week. So what we then want to do is to have an x log y. What is x log? Yeah, you can do that twice. I did too many different. I made too many changes without committing. mine is that. Probably. What is the thing called? X. Oops. X. Well, just X logs Y. Two inputs X and Y. Y is labels. And then the other one is the outputs. Plus wow, compiles. Yeah, and then we need a derivative loss function. Where did I do that? Use that rather. I think it's something with dividing by m and a 2. And I don't drop out, so that has to do with the alpha. Not with the forward, of course. So it's the backwards. This is running already. Fuck, I miss it. Filtering samples. Forward propagation. Where's my backwards propagation? Oh, yeah, backwards. Two times the residual. That's definitely the derivative. So yeah, de is dat al. Ping, ping, ping. Training, that's it, yeah. Derivative of the loss function. That is the initial key. And then we need for that this minus, also a negate. I'll just sub those differently. Subtract or sub. No, I'll just use the same thing as above, but then differently. Here's the loss function. Negate stuff. Whoop. So we do negate and then sub. And then not the log of, oh here it is, y log, but it is now y divided by. So the x log y changes into a divide. Divide, or whatever it is that I should use. And the rest is the same. It's definitely sub, because we already had that one. So either it's diff or divide. I think divide. One not. Did you mean device? Oh, come on, man. What about diff? It's not divide. Okay, there's a definite problem here. What if I'm trying to divide by 0 here? Not a little bit. Potentially also on the other side. I can't just divide by... Oh, it's a predicted probability. Wait a minute. I should be dividing through the output then. Oh, that's what I'm doing. Right. like literally here, I bet. Return 0 if x equals 0. Yeah, well, this is the one that we need. That's just the opposite of the x log y. Let's just use that one. So that's called x div y. It's indeed not exactly what I wanted, because you can still divide by 0 if the... Yeah, well, but... yeah. Theoretically, the output should never be really 0, right? But it's... I think with a round off, it bloody well might be. I think the trick is that you have to just manually... I'll just do this calculation, and then I can replace all nonce, not a number, with something reasonable. Which I bet is quite straightforward. But let's just run this. And I have to go eat, so... even if it fails, I should not... What if it... I'm going to eat. But I want to see it running. X div y suddenly does not exist. X div y. Oh, okay. Well, we can do that before I go eating. Yeah, that's how it starts. Compile, damn it. You want me to starve or something? This compiler has no compassion. Oh, this. Crash. Totally crashed. Shit. Oh wait, yeah. It's not too bad. Asking for a tensor of 1 dimension from a tensor of 2 dimensions. But we don't know where we were at the moment that happened. Let's just make a guess. No way, output's changed. Output 1.9, no. Why do I have to guess this? Is it this line? I'm going to eat. It's not working. I don't know why. The dimension of this thing changed probably, but I don't know. Oops. If we run this, then what happens? Did it print stuff or? This will sort of crash. It still doesn't work. So it was not it. It was not it. Xi1 still has 2 dimensions here. That's not it then. Then what is it?